Earth, or the age of the Sun, or the age of the universe. It is only about 300 million years, a short time, astronomically speaking. And so these systems, like the binary pulsar system, should be generating gravitational waves, and at least some of them must be getting close to the point where the two stars will be almost touching. And at that point, the gravitational waves get very much stronger. There is yet another type of gravity wave observatory that is being considered for construction. And the next slide will show us that. This system is referred to as LISA, the Laser Interferometer Space Antenna. It is a joint project of the U.S. National Aeronautics and Space Administration, NASA, and the European Space Agency, ESA. The hope is that it might be orbited, put into orbit around the year 2018. That date has been slipping recently, in part because of the recent economic downturn, and it's not clear that that date is going to be precisely fixed, but in any case, it's still very hopeful that this project will take place at some time in the future. This system will be sensitive to lower frequencies than the LIGO, Virgo, GEO, TAMA projects on the Earth. It will also be very sensitive to the orbiting pairs of neutron stars, as well as orbiting pairs of black holes, which are believed to exist in the centers of many galaxies. A very exciting prospect for cosmology and for astrophysics in general. Well, I hope in these remarks I have given you a flavor of a particular experiment, one in which theory and experiment were very closely interrelated. We couldn't have done the experiment without the theory to give us hints on exactly what to look for. And the theory by itself existed for many years, more than half a century, between 1915 and when this binary pulsar was discovered, with apparently no hope whatever of ever being able to confirm the presence of gravitational waves, because a laboratory experiment seemed to be entirely out of the question. Fortunately, in this case, the astrophysical discovery made possible an experiment which could not have been undertaken on Earth. Thank you very much for your attention. I've enjoyed speaking with you, and I look forward to our interactions later in the week as well.
Professor Peter will take some questions from you. Do you have questions?
Please. Okay, question here from Iceland.
You briefly mentioned the magnetic fields of the neutron star. How is it originated if it's constituted by neutrons, which are neutrons?
Good question. The question was, I remarked briefly on the presence of very strong magnetic field, essentially a dipole magnetic field, rather like the Earth on a neutron star. And the question is, so where does the magnetic field come from? We don't have anything there that's going to generate electrical currents like you would have in a coil or something to generate a magnetic field. The answer is that magnetism is present in many, many places in the universe for quite natural causes. The Earth is one example, of course. The Sun is another. The Sun's magnetic field is dominated by surface effects that we see in sunspots and other things like that. But if you cause the Sun to suddenly shrink to the size of a neutron star, as these neutron stars have done during the supernova explosion of the star that was there previously, you essentially compress the magnetic field, whatever it was, to a much smaller region, and that magnifies it. And that magnification is, it's something like, well, it's conservation of flux is a very rough way of putting it. And anyway, that can turn out to create very strong magnetic fields. The interior of a neutron star, despite the fact that the whole object is dominated by nuclear matter, it is not true that even though neutrons are uncharged, the center of a neutron star is believed to be not only a good conductor, but a superconductor. And so once you have some magnetic field in a superconductor, it will be frozen in, and it will stay there for a long time. We can, by looking at the changes in the rotation period, that is not the orbital portion, but the spin period of neutron stars, we can tell that the magnetic fields are not decaying at any significant rate. Once again, we can measure this with a very high precision because of the clock comparison aspect of the experiment. Another question? Is one here? Here comes the microphone. There we go. Good.
I don't know if this is a complicated question, but you've talked a lot about gravitational wave detectors. How exactly do they work? Are they like radio antennas? And or is there anything that oscillates when the wave arrives at the detector?
Good question. He was referring to the gravitational wave detectors that I mentioned just at the end. LIGO, Laser Interferometer Gravity Wave Observatory. What do these things mean? It means that the basic detector system involves a laser signal being sent from one point to another distant point about 4 kilometers away. At each of these ends, are large masses suspended by a system which essentially isolates them from seismic noise caused by the shaking of the Earth. There are two elements to the interferometer. One goes this way and one goes this way, so they make a right angle. And basically the laser interferometry allows the distance between mass A, mass B, and mass C to be measured very accurately as a function of time. If a gravitational wave goes by, there will be a little oscillation in the positions of the outer masses owing to the shifting and expansion of space. In fact, the pulsar experiment is almost the same. After all, we are measuring changes in the distance from the pulsar to the Earth effectively by using a coherent signal rather like the laser signal in the laser interferometer system. I think your experiment today had some interferometry in it as well. Yeah, I haven't seen the problems, but that was my understanding. Anyone else?
Well, so in the experiment, you can't measure just the difference in the length of the orbit because it's so small, it's just 1 millimeter. But you can measure the difference in the period. So what kind of time difference is that? How big is the difference?
Well, I got everything except the last point. You're right that the shrinkage of 1 millimeter is not a distance that we can measure usefully, but we can measure the shortening of the orbital period, and we measure it largely because it is a cumulative effect. Each successive rotation is a little bit shorter than the one before, and we measured this now over 35 years. So that's many, many orbital periods, and it builds up to an amount which is, as you saw on the one graph, is now about 35 seconds. Now, have I missed one part of your question in the end? No. Okay. Please go ahead.
I would like to know what happens when the period of rotation shrinks so much that the neutron stars touch each other. Will they blow or will they merge and create a supermassive neutron star? Or what will happen?
Yeah, very good question. The question was, so what happens when these two stars run into each other, or almost run into each other? So the answer is, a big splat. It's going to make a mess. The two stars will be, well, first of all, when they're in a very close orbit, say just a little bit more than, separated by just a little bit more than their sizes, so they're not quite touching, they will begin to be substantially elongated in the shape of an American football, say, because of tidal effects. Eventually, at this point, they're so close that the gravitational radiation is very much stronger than it is right now, and so these effects are happening quickly. In the last few seconds, the period will go all the way down to about a millisecond before the final event happens. The final event itself is a coalescence. The two stars will merge into one. The one object will therefore have a mass of 2.8 times the mass of the sun, minus whatever is carried away in the form of radiation, which is significant, but it's not a substantial fraction of the total. So say it's 2.4 times the mass of the sun still. That's larger than the maximum mass believed to be possible for a stable neutron star. Neutron stars are supported by a quantum mechanical effect known as neutron degeneracy pressure. Neutrons are quantum particles, and therefore you cannot have more than a certain number of them in a certain region of space, basically. And anyway, so neutron stars have a maximum possible mass. Anything above that, the gravitational force pulling it in will exceed the neutron degeneracy pressure and will cause the star to collapse. What happens if a neutron star collapses? There's nothing else known that will save it from becoming a black hole. So we believe that black holes of mass about 2.8 times the mass of the sun would generally be created at the endpoints of the evolution of systems like the binary pulsar system.
Well, is the process of the creation of the neutron star and the black hole is the same like supernova? Because a supernova always follows two paths. Either it turns to a white dwarf or a neutron star, or it turns to a black hole. So what's the difference in the process of evolution?
Okay, I hope I understood enough of your question. It was about the supernova that creates the neutron star in the first place. Our understanding of the phenomena of supernovae is that they occur in stars which have initial masses, probably 10, 12, 15 solar masses, somewhere in that range. So stars substantially bigger than the sun. The sun will not end its life as a supernova. It will end its life in a somewhat less glorious way by swelling up to become a red giant and then eventually losing some of its outer layers and becoming a star known as a white dwarf. But these more massive ones, 10 or 12 or 15 solar masses, will continue to burn their nuclear fuel in their cores, converting hydrogen into helium by nuclear fusion until the hydrogen is gone. And then the helium will burn to form carbon and oxygen and nitrogen and heavier things up until you get to iron. And there's no further way to go because iron has the binding energy which sort of marks the difference between it being more favorable to have more fusion and being less favorable. The reason we can generate nuclear power by both fusing hydrogen into helium and by splitting the uranium atom into smaller pieces is because at the center, right around iron, there is a minimum or a maximum, if you like. So a supernova occurs when the nuclear fuel is gone. The star can no longer keep itself hot in its core by nuclear fusion processes, and therefore gravity begins to exceed the heat which was causing the pressure to withstand gravity. And at that point, the star can become unstable again to collapse. The core will collapse. It bounces a little bit when it reaches the size of a neutron star and bounces back, and that bounce back will cause the outer layers of the star to be blown off, and something like 8 or 8.5 or 9 or something solar masses will be ejected to form the glowing cloud of gas like the Crab Nebula picture that I showed you, which happened 1,000 years ago. What's left behind in the center then is just the remnant of the collapsed core of a neutron star. Now again, I should ask you whether I really answered the question that you were putting to me. I think I did.
Yeah,
but
you have answered. Thank you.
Good. Anyone else?
Okay, as I know, there is a radiation that we can measure, but if there is radiation, there is a variable. There is a variable magnetic field there, and if there is a variable magnetic field, there is a current, and if there is a current, there are some charges moving. But what are the charges in neutron stars if there are just neutrons? How the current comes from?
I'm not sure that I really grasped your question. The magnetic fields are basically frozen into the neutron star. So as the object rotates, the magnetic field rotates with it.
But
From a fixed point in space, then the magnetic field is moving rapidly. And that generates, that's basically like an electrical generator. A moving magnetic field like that will generate electric potential differences. And that's why noise is generated. In the polar regions, charges are removed from the surface and caused to be accelerated by this large potential difference. They stream along the magnetic field lines, which are curved, and that curving motion of the charges, since it accelerates the charge, it means it has to generate electromagnetic radiation. That is the radiation that we observe with the radio telescope at a great distance halfway across our galaxy.
Here, over here. So far as I understood your explanation, you calculated the loss of energy of the binary pulsar, and then made it match with the graphs of the gravity waves. That's how you knew that it was missing energy and it was like Berman Einstein's theory. Am I right?
I'm sorry, I didn't get very much of that.
When the binary pulsar rotates, it loses energy, and you calculated the energy that it had to lose, and you could measure that in the gravity waves, and that's how you found out what was going on. Am I right? That it was the orbit was getting shorter, and the time was getting shorter as well. But at the beginning of your explanation, I believe you said the
transmitter that is in the orbit of the pulsar, not at the receiving end. The signal is, of course, conveyed from the transmitter to the receiver electromagnetically. No gravitational waves are involved there. The gravitational waves are involved in changing the orbital period at the position of the pulsar. Now, if I have not answered your question, please come down and ask me after we're finished.
I wanted to ask if there was any evidence that the gravity waves could be connected with electromagnetic waves. I mean, for one unique radiation or something like that.
Good. The question was, what are the connections between gravitational waves and electromagnetic waves? Are they related in some way? The answer is yes, certainly there are many parallels, but there are also some significant differences. The differences arise, you generate electromagnetic waves by accelerating charges. You generate gravitational waves by accelerating masses. Charges, however, come in two flavors, positive and negative. Masses are always positive, and therefore dipole gravitational radiation cannot exist. And that means that the lowest multipolar expansion of gravitational waves is the quadrupolar term, and the coefficient of quadrupolar terms is always much less than the coefficient of dipolar terms. That's one of the reasons why gravitational waves are so weak compared to electromagnetic waves, for which we observe primarily the dipolar effect. Okay. Why don't we ask him while you have the microphone? Go ahead.
Thank you. I'd just like to know if there were ever any alternative mechanisms proposed for the shortening of the orbital period rather than gravitational waves, because the theory it's fine.
Okay, that's a very good question. Also, pass the microphone forward because someone else has a question here. Very good question also. The question was, okay, so the system may be shrinking at a rate that's consistent with what Einstein would have predicted for gravitational waves. But still, how do you know it's gravitational waves? Couldn't it be something else? Couldn't it be some other energy loss mechanism that just happens to come out at the right value? The answer is yes. In principle, you could imagine other possibilities. And in the late 1970s, shortly after this pulsar was discovered, and it became, we got excited about the prospect of being able to measure the gravitational wave effects. Many people worked on problems to see what other effects might be significant. For example, if there was a significant density of dust or gas in the system where these stars are orbiting, that would be a source of friction, would slow them down and lose energy and so forth. Then you can work that out and know a reasonable amount of that material would cause the amount of damping that we see. Electromagnetic coupling between the two stars, it's easy to rule that out. They're too far apart for that to be effective. What about tidal effects or rotational distortion of the two stars? You can work that out. It's not important. So basically, we and others tried very hard to do the necessary calculations to see whether there would be any likelihood of competing effects that might give something of the same order of magnitude as the expected gravitational wave effect. And the answer was none was ever found. Furthermore, when the experiment progressed to the level where the experimental precision was getting better and better, as the delay curve farther down, the uncertainty in the rate of orbital decay was first around 20%, and then 10%, and then 50%, and then 1%, and now it's about 0.21%, 0.2%. It's really not even thinkable that the experiment could be giving the right answer for the wrong reason now, and so we stop worrying about it. I think that's very unlikely. Okay, let's go.
Stephen Hawking radiation predicted to be emitted by black holes. Is that radiation?
Stephen Hawking predicted that black holes would evaporate when they become small enough. They can lose sufficient fractions of their mass by quantum mechanical effects at their surfaces. That was not gravitational radiation. That was the loss of actual particles, gamma rays, and electron and positron pairs. A different phenomenon entirely. Okay.
What do you think might be the effect of gravitational waves in the beginning of the universe?
Yeah, one of the hopes of the experiments like LIGO, Virgo, GEO, and especially LISA is that they will be able to make measurements of gravitational wave effects that happen very early in the universe, near the time, shortly after the Big Bang, when material was being clustered into the regions which today form the galaxies and so forth. That would create a significant gravitational radiation which might be detectable by those instruments today. There are many reasons why, for astronomical and cosmological purposes, these gravitational wave experiments with detectors on the Earth or orbiting in space could be very significant. They'll be opening a new window on the universe using first light for many years, then radio waves, and X-rays and gamma rays, sort of cover the electromagnetic spectrum now, and the hope is that we will be able to cover a portion of the gravitational wave spectrum as well. I think we probably should line this up soon, but let's do, okay.
Okay, I don't speak English very well, but I have to be clear as possible. You said that pulsars are objects with a lot of mass in a really small space. How can this be possible if it's the result of a supernova and star explosion? It's supposed that most of the mass go out of space.
Are you asking why
Why there's a lot of mass in a little space? It's a result of explosion.
Yeah, well, the core of the system is the part of the star which had exhausted all the material except for
Gravitational waves on binary pulsars. Didn't you do it with any two stars turning around each other? Do they have to be pulsars?
You'll have to give it to me again a little slower. I didn't get the question.
Why do you study the effect of gravitational waves on binary pulsars? Couldn't you do it with any kind of star? Just two stars turning around each other?
Good question. The question was why do this gravitational wave experiment using an orbiting pulsar? Could you not use other stars as well? The answer is no, not really, because the pulsar very significantly acts like a very accurate clock. Right? We get a pulse of radiation precisely every rotation of the star. The star is very massive, very dense. It's a rigid sphere rotating rapidly. It doesn't lose energy to its own rotation, and that means it keeps very good time. Ordinary stars have spectral lines. We can look for Doppler shifts in the spectral lines of an orbiting star, but that's not precise enough, that's not accurate enough to give measurements of the precision necessary to do the gravitational wave experiment. So I described the experiment at the beginning of my talk as a clock comparison experiment, and the reason it works well with an orbiting pulsar is because the pulsar is such a good clock.
Thank you.
Thank you again, everyone.
Sibi Shaltun.
City until 1230, which is the time when my band rose as more important. Pero se sabe que la gente estuvo aquí hasta la llegada de los ferrocarriles, like 1500, 1600, la gente estuvo aquí. But it is known that they were here until the arrival of my band. That's why we see the chapel. Por eso tenemos la capilla que fue construida para convertirlo en las imágenes anteriores.
¿Ya las habías guardado?
Sí, las tenía en la computadora, ¿no?
¿Estamos con contactos? La neta de fútbol. Hola, guapa.
Hay una guerra entre Francia y España. Y España dentro de los franceses. Una pequeña guerra. Entonces el Papa, como medalla de honor a los españoles, les autoriza solamente
Míos del acuario, cuando toda la mano viene no me da cosa. Es que si estás, pero tienes las dos esperas que me da costumbre.
estás limpiando y te van a dar.
Los calades son los que te muerden.
No te estreses.
Hay iguanas por todos lados.
Me voy a raptar.
No, sí tomé fotos, pero el video sale mejor.
La foto. No, de los flamingos no hay ninguna foto en la...
¿Ah, no?
En la cámara, no. Uy, hay un chorro.
Cenote Shlaka.
Hoy es viernes.
Vamos a rodearlo y ya nos encontramos del otro lado, allá en la sombra de los árboles. Y vamos a ver otros
Aramis va como en el de México. Paseo, ¿verdad?
Hola. How are you?
Good, how are you?
I'm fine. Let's take one picture. Okay? Would you mind?
No, sure.
In what direction? I don't know. So you look good today. Have no headache?
No,
I'm
good. What about you?
I'm fine.
Pero pueden ver esa
Ay,
estructura que
me atravesé.
De donde 3 veces al año, no, 6.
No, cada 3 meses.
Ah, cada 3 meses, sí.
sí. Entonces, miren, esta pirámide la encontró la National Geographic
Sí.
dentro de otra. Cuando ellos quitaron la otra, la encontraron.
Todo el susto que les han de haber metido a las personas, eso no se hace.
¿Por qué no?
Pues porque no, porque es una falta de respeto a la paz de las personas. Ah, que va a explotar.
Ujú.
Así. Vamos a rodearla, ¿no?
Ujú.
¿Sí? ¿Aquí es donde ocurre eso?
Maybe.
So,
¿No quieres dormir?
Sí.
Hola, Javier. ¿Cómo estás? ¿Ya conocías a quién?
cuando estaba chico, pero pues no me acuerdo. Sí.
Ya me quiero ir, ya me aburrí.
Piedra.
Sam strašno fizikálne predstavy si veľká forma. Znam fyzika.
Molte affermazioni ci sono anche di chiaro.
Pero se
Igual no te la choza, pero con nudo y
Gracias. Y de aquí, de la bóveda central, grabamos hasta arriba.
¿No lo viste la vez en la playa? Aquí me dedicaba.
Rancho Tierra Bonita.
¿Te metiste? ¿Sí te metiste?
Claro.
¿De verdad?
Ahí yo voy a jugar, muchachos.
Bueno, ¿cómo la foto?
Fíjate, Elisa.
Here we have from Rancho Tierra Bonita. We would like to welcome every one of you to this wonderful place and this beautiful day. Say hello to Pastor, Arturo, Carlos, Adrián, Don Curco, Toño, every one of them. Queremos darles a todos nuestros hermanos y amigos latinos la más cordial bienvenida a Rancho Tierra Bonita. Nuestros charros de la Asociación de Charros de Yucatán quieren darles una muy calurosa bienvenida a este su rancho, Rancho Tierra Bonita. El día de hoy vamos a darles un espectáculo ecuestre digno de este país. Recuerden, amigos latinos, que la charrería es el deporte nacional, es nuestro emblema. Estamos muy orgullosos de que los charros nos representen a través del mundo. Ellos se van a preparar
Con Amaranta que nos habló para que fuéramos.
Ellos se están preparando para su primer estampa, que es el desfile de la reina.
Ya hablé con Pina finalmente,
¿Hoy?
sí, ya me hago un celular y eso.
Al celular de... ¿Y qué te dice?
This is their first stand, the flag salute. With all due respect, the brother countries will come to you and say hello and welcome.
Ya se enteraron en mi casa. Fíjate que en Cuba nunca se ve luz. Se van a recibir, vaya.
Pero ¿cómo está eso que...?
They are performing now what we call in Mexico a crisscross. Great coordination.
Het zijn wel een beetje ponies, hè?
Ay, 10 puntos de venta, algo así.
Pero ya fue 10 más 10.
No, y se subió más. Él logró subir más el 19 porque habían cosas que había puntos que no merecían todavía. No, todavía no sé bien.
O sea que fue más de 28.
Ja, zeker ook zo lang geleden.
Está contento.
No, genial, me estaba hablando ahí. En Cuba, lo que siempre se pone con mención.
Dat is paardje volhouden, zegt deze.
Nunca nadie en la Olimpiada había sacado plata.
El oro también está bastante bacano. No, pero qué cosa, si hay contento de premio. Me llevé de la prepa un oro, un libero.
Unas palabras de uno de los ganadores. Sí, eres una estrella.
Cuba, viva Cuba. Wow. Hasta aquí mi primera racería de la vida.
Medalla de plata en las 40 Olimpiadas de Física.
En la Olimpiada Internacional. 40avo. Ay, qué calor ha de tener esa mujer.
¿Te lo escribí o te di un papelito? ¿Te di un papelito? Olvídate de eso. Olvídate de eso. ¿No has visto cosas de estas?
Kijk, het is wel heel stevig getouwd. Kijk, het heeft nog steeds een klimming van die haspen die hij heeft.
¿Te gusta?
Y me levanté con un sueño, una bobería así. Hice así, me metí
Ik dacht dat ze hier maar van die twee bammetjes in het touwtje deden.
Ahí dan,
maar meen ik.
No toqué el suelo, viene para mantear y se hundió el lado. En el lado ese, todo el mundo me dijo que no hagan nada. Sí, pero había una gran parte que la gente se apoyaba con una mano, una piedra. Yo pensaba que no, yo pensaba que iba a ser entregado.
En mi tierra mexicana hay un cielo sin estrellas y no hay hombre que se raje ni mujer que no sea bella. Las del centro son altivas, las norteñas son sinceras, las orianas sensitivas, todas hembras muy de verdad.